Hello, everyone. As you can see, I'm not our president. Emma's on leave at present, and as a vice president of the RAS, I've been asked to take her place today. Our first speaker this afternoon, who is Tom Collette from Portsmouth University. Tom is the winner of the RAS Winton A Prize. If I could ask, please, that you send your questions to Pamela Rowden at the end of Tom's talk, and we will have 5 minutes of questions after Tom's talk, and that will then be followed by early careers poster completion winners, their talks, and questions at the end of all of their talks. So after Tom's talk and then after all of the other talks. Thank you very much. If I pass over to Tom, if you want to share your screen.
Hello, thank you very much for having me. And firstly, thank you very much for the RAS Winton Award last year. That was a real honor and privilege to receive. So I thought today I'd tell you a little bit about measuring the curvature of space-time. So as you probably know, in our solar system, the orbits of the planets are on ellipses around the sun. There are perturbations that come from when those planets gravitationally interact with each other. But in a system with just the sun and one planet, you would expect the planet to be orbiting in an ellipse. And that drops naturally out of Newtonian gravity, the law of gravitation, that the force of gravity goes as 1/r². However, that simple picture that planets go on ellipses is slightly wrong. Indeed, it's been known for quite some time that the perihelion of the orbit of Mercury advances by about 2 degrees per century. That means that instead of the orbit being on a fixed ellipse, that ellipse is slowly rotating. And you don't get that in Newtonian gravity. If the force goes as 1/r², then this simply shouldn't happen. So it was known that 1/r² seemed to be in some ways wrong as a description of at least some of the observables in our own solar system. And it was Einstein's theory of general relativity that came up with a neat solution to this. In general relativity, it's a theory of gravity where you introduce a space-time that is deformed by massive objects. When you write down the force law for what you get for gravity in GR, you get that the force it goes as Newtonian gravity plus some terms that go as 1/r³ and higher order. Now, what that means is that for large distances, for the orbit of Jupiter or the orbit of Pluto, that Newtonian gravity is pretty much sufficient to describe the orbit. But as you go closer to the sun, making that r term smaller, then the deviations from Newtonian gravity are seen, and that is why the precession of the perihelion of Mercury is observed. So this was a great sort of post hoc demonstration, justification for general relativity. But what was really needed in the early 1900s was a predictive falsifiable test that GR made that was different to Newtonian gravity that could be used to validate or disprove general relativity as the correct theory of gravity. So this is where gravitational lensing comes in, which is what I've done a lot of my career of my research on. And the reason that gravitational lensing is interesting is that it's a prediction from general relativity that's different to Newtonian gravity. So what you're seeing here in the middle is a massive elliptical galaxy. It's so massive that it warps space-time by a huge amount, such that light passing close to this galaxy is deflected in this case by about 5 arcseconds. That's a 60th of a degree. And there's a second galaxy in blue, a second blue galaxy, almost aligned perfectly with this foreground massive galaxy, but much more distant. And so the light rays coming from that background galaxy are distorted and deflected into this Einstein ring. You're seeing multiple images of that background galaxy heavily deformed. And the reason that this is that these objects are interesting as a test of gravity is that in Einsteinian gravity and in general relativity, you expect twice as much deflection at the same mass of lens as you would have got using Newtonian gravity. So this is a prediction that comes from GR that you can use to test it. The reason that you get different deflections is essentially that there isn't this curvature of space-time in Newtonian gravity. So if we want to test this, then we need two things. We need to know the actual mass of the deflector, and we need to be able to measure the size of the deflections. The way we can learn about the mass is to use a non-relativistic tracer, a particle moving much less than the speed of light. So the motions of planets within the solar system, or the motion of stars within a galaxy, that can tell us the mass. And then by observing this, the Einstein radius, the separation between images in this blue ring, you can work out what the deflections are of the light, and you can infer what the curvature of space-time must be around this galaxy. So the problem in 1919 was, or in 1915, when GR was first postulated, was that these gravitational lenses were vastly too faint to be observable. Indeed, they weren't discovered until 1979. And in fact, Einstein thought that these would never be observed. So the Einstein rings that I was showing you there were not a viable test of general relativity in the early part of the last century. However, what was observable in the 1900s, indeed, even before that, was both the sun and the stars. Now, the sun has mass, and indeed, when you calculate the deflection angles that you should get from the sun for a star that appears very close to the solar limb on the edge of the sun, then you expect in GR to have a deflection that's about 1.7 arc seconds. In Newtonian gravity, it should be half of that. So what you can do is you can do an experiment where you observe the positions of the stars in the night sky, and then 6 months later, when the sun is directly in front of these stars, then you expect the positions to be moved by about 1.7 arc seconds, moving further away from the sun. As you go to large distance from the sun, then you don't see any deflections. So really, the bulk of the signal is looking for shifts in the positions of stars very close to the solar limb. So you could do that experiment. You could get your telescope, look at the sky, look at it again 6 months later. The problem is, of course, that the sun is incredibly bright. And so I really don't recommend that you look at the sun through a telescope because you will not be able to test for the curvature of space-time. You'll damage your eyesight or your camera. So instead, what you needed to do, and this is what was the core of the 1919 Eddington expedition to test this, is to observe the positions of the stars close to the solar limb during a solar eclipse, where you have the moon blocking out the light of the sun, such that you haven't got that contrast problem of the sun being vastly brighter than any individual stars. So back in 1919, as I said, Arthur Eddington wanted to test this prediction of general relativity. And I believe that this expedition was funded by the Royal Astronomical Society, sending two teams, one to Sobral in Brazil and another to the island of Principe off the coast of West Africa to measure the deflections of stars near to the solar limb. This is an image of the 1919 eclipse, and this is the same or a similar image shown in the negative, and you can maybe just about faintly make out these dots, which are the positions of stars. And it turned out that the deflections that were observed were completely consistent with that 1.7 arc seconds predicted by general relativity, and inconsistent with the value of half of that Newtonian gravity had predicted. So this was sort of the sort of moment, the instant at which Einstein and his theory of general relativity really became a household name. This demonstration that general relativity had made a falsifiable prediction and had come out and passed that test. Since then, we've managed to test these deflections and similar effects of general relativity in the solar system to really incredible precision. So the most precise measurement of the validation of general relativity comes from the Cassini probe, and measurements of the light travel time between the Earth and Cassini when it was orbiting Saturn back in 2002, when the Earth, the Sun, and Saturn were almost perfectly in a line in a conjunction. So as the conjunction went along, Saturn passes along this line with the Cassini probe getting ever closer to the solar limb until it starts to move away. And what that means is that as the light is traveling closer and closer to the solar limb, it's feeling stronger and stronger general relativistic effects. And so what you get is a time delay introduced by general relativity. And this is the data that came from Cassini. The gray boxes on here are the measurements, and the gray line on here is not a fit to the data. It's the prediction for the change in the light travel time as a function. It's the prediction from general relativity. And the cool thing is that this data is so precise and so accurate that that general relativity is validated to be correct with an uncertainty of about 2 parts in 10 to the 5. So to all intents and purposes, we know that the way that space-time curves is what general relativity predicts on the scales of our own solar system. However, we don't actually have very good measurements of how space-time curves over longer length scales, or where you have a more massive object than just the sun. It's incredibly hard to make these measurements, and I'll be telling you about a precise measurement in another galaxy. But let me first tell you why it's perhaps interesting to ask the question, could there be deviations from general relativity on longer length scales than just inside our solar system? So you're probably aware of the accelerated expansion of the universe, the fact that when we look at supernovae as a function of redshift, as a function of the expansion of the universe since those supernovae exploded, what we see is that the expansion is speeding up. The supernovae are not at the distance that you would have expected for a universe that was entirely made up of baryonic matter and had no spatial curvature. This lower plot shows the residuals from the Nobel Prize winning supernova cosmology experiments, the Supernova Cosmology Project, and the High-Z Supernova Search Team. And this dashed line in the bottom shows the best fitting model to the data that doesn't need to introduce cosmic acceleration. And it's pretty strongly excluded by this data, and more modern analyses, adding more data and adding different data sets, shows overwhelmingly that there is evidence for cosmic acceleration. So to solve that, if you assume general relativity is correct, then you need to introduce some weird fluid that we call dark energy, something that we don't understand very well and that we don't really have a physical motivation for, other than the fact that we need to add it in to solve this model. Now, alternatively, you can introduce not deviations to the contents of the universe, not adding a dark energy fluid, but you can also have universes that naturally where the expansion accelerates, where you throw away GR and instead introduce theories where the curvature of space-time is scale dependent. So these theories are interesting in the sense from an Occam's razor standpoint, in that whilst you are complicating your theory of gravity, you're hopefully simplifying your theory of the contents of the universe. So what we need to do to test this is to really see, can we see how the curvature of space-time varies as a function of scale? We know that it needs to be the correct, that we need to get the solar system tests, GR needs to be correct on solar system scales, but can we test models on longer scales or on different mass scales where we can look for deviations from GR that might be or that would be a sign for modified gravity? So I wanted to do this on the scale of an entire galaxy using gravitational lenses. It's actually incredibly easy to work out what the amount of spatial curvature around a gravitational lens is. You can almost do it on this slide. If I had a scale bar on here, you would be able to put a ruler across and say that the Einstein radius, in this case, is about 5 arcseconds. That tells you precisely how much spatial curvature there is here. But the problem is actually working out the spatial curvature produced per unit mass of the lens. It's actually quite hard to look at a galaxy like this. This one's about a gigaparsec away. How do you work out how much mass is in that galaxy? So to answer this question, I used a lens called ISO 325-G004, a really memorable phone number, that one, which is a massive elliptical galaxy about 140 megaparsecs away. The reason that this is interesting compared to other gravitational lenses is that it's about a factor of 10 closer than the typical gravitational lenses. And when I started this project a few years ago, this was the closest known example of a strong lens. Now, this might not look to you like a strong gravitational lens. You see the massive elliptical galaxy, but you don't see the extended arcs, the rings of that background source. The reason is that this lens is incredibly close, and so it's incredibly bright. You have a contrast problem. But with the Hubble Space Telescope, if you zoom in on the center, fit a light profile for the galaxy and subtract it off, then what you find is that buried under that orange galaxy is this faint blue arc system coming from a galaxy that's 1.7 gigaparsecs away. It's at redshift 2 and a bit. So we've now got a gravitational lens that's close enough that we can really try and study the mass of the lens. The way that we can do that is by looking at how fast the stars are moving within the lensing galaxy. So this figure here shows the velocity dispersion for the stars within that lens galaxy as a function of their position, with 0, 0 being the center of the lens. The color bar here shows you that in the very center of the lens, the stars are moving typically at about 400 kilometers per second, and then they're falling off as you go further away to be moving about 300 kilometers per second. Now, this galaxy is not so close that we can actually resolve the motions of individual stars. These properties are very much an ensemble statistical average. You can think of it kind of like you might think about temperature for a gas. We're not measuring the speed of the individual atoms, but we can measure the temperature of the gas. And so this is really telling you about the typical speed of the stars. But that's enough to teach you about the mass of the lens in the same way as you can think about if you have a ball on a string and you twirl it around. The faster you twirl that, the harder you need to pull on the string. You need more centrifugal force to keep that ball on its orbit around you. And similarly, you need more mass to pull the stars in to let them move more quickly. So now we have what we need to test the curvature of space-time, a gravitational lens telling us what the photons are doing, telling us about the curvature of the space-time, and the stellar kinematics of the lensing galaxy, looking at the stars to tell us about the mass within the Einstein ring. So to put these two things together, we need a model that we can fit for. And so the sort of sensible model to use for this is to say that the stars are where we see the light, allowing for some free parameters that allow for variations in the mass to light ratio as a function of distance. Then we need to embed these stars within a dark matter halo that we can get from cosmological simulations of how dark matter clumps. And finally, we need to add a supermassive black hole in the very center of the galaxy. Supermassive black holes typically have about 1% of the total baryonic mass of a galaxy. So you don't expect this to make a huge impact on the lensing, but you do expect it to have a fairly large impact on the motions of the stars in the very center of the galaxy. And so that's why this needs to be included. And then the final parameter of the model that's important is actually the amount of spatial curvature produced per unit mass. So this is essentially a normalization that connects the amount of lensing you see with the amount of dynamical mass that you need to explain the motion of the stars. So I'm calling that parameter gamma, and that gamma is 1 in GR, and 0 it would be in Newtonian gravity. So the cool thing is that model is able to reconstruct the data. This is a reconstruction of the kinematic data. You can see it basically gets down to the noise, reproducing those features of the stars moving faster in the center and slightly slower further out. To do that, the dynamical mass of this lens within the Einstein ring is about 1.4 times 10 to the 11 of the solar mass. So this is one of the most massive galaxies in the universe. You don't get many galaxies much more massive than this. And to explain it, I need a black hole that has a mass of a few times 10 to the 9 solar masses. So typical, consistent with that picture, that black holes are about 1% of the total mass of a galaxy. That same model simultaneously is able to reconstruct the lensing data. You can see the data, the model, and the residuals. The residuals get down very close to Gaussian noise. And as a nice bonus, you get an image, a reconstruction of what the unlensed source galaxy must have looked like. In this case, you get a sort of extended feature, extended smoother feature. And then there's some really highly magnified star-forming clumps that are resolved because you actually get some really extreme magnifications of this arc here. This arc is actually entirely composed of images of this clump, whereas these two arcs are images of the whole system. Anyway, that's the astrophysics of the source. It's kind of a nice side product, but the cool thing is that the final parameter of the model is that gamma parameter, the validation of general relativity or the test of it. And the result that comes out of it is that to be able to simultaneously reconstruct both of these data sets, the spatial curvature per unit mass must be consistent with the general relativity prediction of 1. The value comes out at 0.97 with a total error bar of 0.09. And that error bar is mostly dominated by our inability to actually measure the stellar kinematics to extreme precision. There's about a 2% uncertainty on the speeds that the stars are moving in, and that ends up mapping to this. Well, that ends up being 8%, 0.08 of this uncertainty here. As a nice astrophysics aside, the interesting thing that came out in terms of what the stars must be doing in this lens, the mass to light ratio in this lens is consistent with a Milky Way-like mass to light ratio at large radius, whereas at the center, there's about twice as much mass per photon that we receive than you would have expected if the initial mass function of the stars were consistent with what we see in the Milky Way. Anyway, that's the end of my talk, the summary. Hopefully it was accessible and of some interest. By combining imaging data from the Hubble Space Telescope and spectroscopy from the Very Large Telescope in Chile for this lens, we were able to show that the spatial curvature of the curvature of space-time per unit mass is consistent with the prediction from general relativity over a 2 kiloparsec length scale. So vastly larger than the few AU length scales that are tested in the solar system. Thank you.
Thank you very much, Tom. Nicely on time. And before I hand over to Pamela Rowden for the questions, I should have said at the very beginning that you should note that this meeting is being recorded, and you should see at the top of your screen a small green shield, which means that you're using the most up-to-date version of Zoom and that it's secure. So perhaps if I pass over to Pamela now, who should have collected any questions for Tom.
Okay, please send me your questions in the chat. Okay, Tom, how long had you been working with this particular galaxy?
Yeah, so this this galaxy was discovered about 15 or so years ago. And I sort of first got interested in it to do this measurement back in 2016, I think. So we wrote the proposal to the VLT, said that we would need, the Hubble Space Telescope data was in hand. So we then asked for VLT for, it actually only takes an hour of observing time on the Very Large Telescope to get the data we needed to do this. Got the telescope time, the observations were taken, I think, late 2016, and then the analysis took a couple of years. So we actually have data for another 10 such lenses that we're working on at the moment, slightly more distant so that we can test different scales, but also to try and improve the precision of this measurement. So it's still ongoing.
Thank you, Tom. Any more questions? No?
The Cassini data. Were you surprised that it was matching so exactly the predictions?
I think not surprised particularly. I think my expectation is that general relativity is probably the right theory of gravity on cosmological scales as well. I think there is a lot of weirdness from the need to introduce dark energy to explain cosmic acceleration, but I think it's becoming very clear now that these modified theories of gravity are really getting pushed into ever smaller parts of parameter space to be able to explain away dark energy. I think it's Cassini was one of the early very, very precise measurements. But I think my personal prejudice was that I was expecting this to be right.
And this leads on to the next question, which is, does your analysis mean that the various attempts at modified Newtonian gravity are null and void?
So it's complicated in the typical kind of modified Newtonian gravity is really trying to explain differences in the motions of stars around galaxies. Most of them are introduced to explain away dark matter rather than the dark energy. At the moment, there aren't really good relativistic formalisms for a lot of these modified Newtonian dynamics, and so it's hard to know what they actually predict for the amount of lensing. What is clear is that the lensing we see, not so much from this galaxy, but from more distant ones, we really do need dark matter. There are plenty of cases where if you just use the baryonic matter, you put the mass where you see light, that does not precisely reconstruct the lensing data that we see. So I think there's pretty strong evidence that unless there's some perverse conspiracy in the observations that really there must be dark matter in the universe as well.
Thank you, Tom. And there's a couple of questions in the Q&A. If you could answer those directly, that would be brilliant, as I understand that we're ready for the next speaker now.
Sure.
Okay, thank you. Thank you very much, Tom. Thank you, Pamela. Okay, so we now come to the section where we have 5 short talks by the winners of the Early Careers poster competition. And if you could please submit your questions in the same way that you've just done, but at the very end of all 5 of the talks. 4 of them will be talks, and the 5th one will be a short video. So I'll pass on now to Sahib. Thank you.
So, first of all, I'd like to thank the RAS for granting me this opportunity to present my research. I'm Soheb. I'm a 4th-year PhD student at the University of Leicester, and I'm going to be talking about the extragalactic wonders of the universe, specifically the migration of compact binaries from their host galaxies. So to start off with, what are compact binaries? When I talk about compact binaries, I'm referring to a system formed of 2 dense objects, such as a neutron star or black hole, which follow the death of 2 massive stars that are at least 8 times more massive than the sun. Now, the reason why these systems are interesting is as the separation over time on the scale of tens of millions to billions of years, the separation of the 2 objects will eventually decrease. And as the separation decreases, they emit gravitational radiation in the form of gravitational waves. So these are perturbations in space-time following the inward orbit of these binaries. And we'll hear more about gravitational waves in Isabel's talk. But following on from this, when these systems eventually go on to merge, we may see some form of electromagnetic counterpart. So we can either see a we may see short bursts of gamma rays known as short duration gamma ray bursts, or we may see multi-wavelength transients such as a kilonova. Now, gravitational waves were predicted 100 years ago, but were only confirmed in 2015 from the detection of a gravitational wave of a black hole merger. But even more recently, the first joint detection of a gravitational wave with an electromagnetic counterpart was made in 2017 following the merger of 2 neutron stars. So this field, at least from the observational perspective, is still fairly new, and observations in terms of gravitational waves aren't plentiful yet, but in the future we should see more. So throughout this talk, I'm going to be exploring the migration of these systems and the properties of the host galaxies. And to do so, I have my special assistant and guest, Neutros, who'll introduce them now.
Hi, my name is Neutros. Thank you for having me. I am a researcher of extraterrestrial life at the Milky Way Citadel.
So when we think of these systems, we'd like to know how frequently they're merging and how frequently the mergers are occurring in the universe. And in order to constrain that, we need to know how far away these systems are. Now, gravitational waves provide us with a constraint on the distance, but unfortunately, with the current generation at least, the uncertainty on the positions are quite large, and the distances at which they can see into the universe are quite short. On the other hand, assuming that most short duration gamma ray bursts come from these compact binary mergers, we have precise localizations for at least a few of them down to a few op seconds. Now, the reason this is important is it allows us to see exactly where these events are occurring on the sky. Now, there are a couple of issues that fold into this when we're trying to determine the distance. Whilst gravitational waves give you an estimate of distance, GRBs don't have this, you can't really do this easily with GRBs. The identification of the host galaxy is very important when it comes to localizing the distance of these events. Now, this has several challenges involved, such as if the galaxy is distant or faint, then when you're attempting to make this association, it's not immediately clear if it's a background source that you can't see or if there's nothing there at all. On the other hand, from the perspective of the compact binary, it's possible that the compact binary may have been ejected from the galaxy at some point during its evolution. As such, when it merges and you get this short duration gamma ray burst, the gamma ray burst will be seen at some offset from the host galaxy. Now, without knowing that this binary has come from the host galaxy, it's really hard to tie the two together. So we can only gauge the likelihood of such an event. And on the right, we have an example of where we have a GRB that's 75 kiloparsecs away from a nearby galaxy. Now, if this binary is traveling at 100 kilometers per second, this could be feasible. But again, there's no definitive way to address this issue.
I remember when I went supernova, I started racing around the galaxy.
So in my research, I aim to emulate these sort of scenarios by seeding simulated binaries into simulated galaxies. I won't go into technical detail, but effectively what this lets us do is it lets us evolve the orbits of the binaries up until the binary merges. And on the right-hand side, you'll see a plot of the sort of trajectory that a binary will take on the XY plane of the galactic plane. Now, when the binary merges, we can then, using these simulations, extract the properties of the host galaxy and the position of the binary at the point of coalescence. Now, this is important, as we'll see later on.
Keep in mind that the environment of the galaxy will determine the kind of stars that are formed. When stars explode via a supernova, they gain a velocity from the impact of the explosion.
So what we find is that the majority of these compact binary mergers seemingly occur in galaxies that are much like our Milky Way. What we also find is that the type of galaxy plays a crucial role in determining how far the binary is able to migrate. For example, dwarf galaxies, which are much less massive than the Milky Way, would allow the binary to travel much further, purely due to, well, this boils down to the fact that the gravity is weaker in general. On the other hand, if you have a greater mass and therefore greater gravity, say in an elliptical galaxy, the distance at which a binary can migrate is much shorter, and therefore there's a higher likelihood that the binary will remain bound to the elliptical galaxy. On the whole, we see that from our simulations that the modal migration of a compact binary is just less than 10 kiloparsecs. And for context, 10 kiloparsec translates to roughly 30,000 light years. And for reference, the Milky Way has a radius of around 16 kiloparsecs. So if a binary were to merge within the 10 kiloparsecs, we would be able to localize it quickly due to the fact that it would overlap with the position of the Milky Way-like galaxy. And this applies to around 60 to 70% of all compact binary mergers that we consider in our analysis. So the future of this, the future of the field is very exciting because we have plenty of missions plans which will not only enable us to peer further into the universe and therefore discover more galaxies, which will aid the associations between SGRBs, short duration gamma bursts, and their hosts, but we will also hopefully be able to detect more gravitational waves further out into the universe and tie them to these short duration gamma ray burst events, which will provide us insight into the stellar aspects and the host galaxy properties that go into forming these events.
I look forward to seeing what the humans will accomplish in the coming decade. Perhaps you'll find more neutron star binaries like mine. Don't forget about my camera star.
So I've left my key points up, but the real take home is that whilst we've made these predictions, they're subject to change based on further observations. Based on whether or not our predictions align well with future observations would tell us how accurate our theories are and whether they need refinement. As with science, this field is constantly evolving, so we'll see in the future how well our predictions hold up. So that concludes my talk. Thank you very much. If you have any questions, please pass them on. So thank you from me and from Neutros.
Thank you for having me. I look forward to future human endeavors.
Thank you to you both. So can we move on, please, to Isabel Romero Shaw, talking about eccentricity in gravitational wave transients.
Sorry, it took me ages to refine my Zoom screen. let me just, okay. Yeah, so hi everyone, I'm Isabel. I am a third-year PhD student at Monash University in Melbourne in Australia. And I am a member of the LIGO collaboration and also of OzGrav, which is the Centre of Excellence for Gravitational Wave Discovery in Australia. And today I'm going to be talking to you about eccentricity in gravitational wave transients. And if you want to see my poster, the QR code in the top right will take you there. So what are gravitational wave transients? Well, gravitational waves are ripples in space-time, and they were first predicted by Einstein in about 1915. So they're caused by huge amounts of accelerating mass. And so far, we've detected gravitational waves from very massive compact binaries, which Soheb just introduced you to. So these compact stellar remnants orbit each other closer and closer and faster until they merge. And Einstein actually never thought we would detect these things because they're really, really small. But 100 years after he made his prediction, we made the first detection. So in 2015, we detected the gravitational wave signal from the collision of two black holes, each about 30 times the mass of the sun, which collided and released a huge amount of gravitational energy, which traveled through space as depicted by this wobbling blue graphic here. So this graphic shows how gravitational waves move through space-time, stretching and squeezing it as they go. So this stretching and squeezing is really tiny. Things stretch and squeeze by less than 1 part in 10 to the 21 when a gravitational wave passes through them. So in order to detect them, we've had to build the most sensitive interferometers in the world. So these detectors are huge antennae. There are 2 in America and 1 in Italy. And they have arms that are 3 or 4 kilometers in length. And we monitor slight changes in the lengths of these arms, which is what happens when a gravitational wave passes through them. And we monitor them using lasers. So this gives us a strain signal, something like what is sketched on the right-hand side of this slide. And the detectors that we have at the moment are sensitive to these waves within a frequency range that is similar to that of the human hearing range. So we can actually convert these signals to sound, and they sound something like this. So what have we actually seen so far with gravitational waves? Well, in their first observing run, LIGO and Virgo, the gravitational wave detectors, reported 11 compact binary mergers from the first gravitational wave transient catalogue. And they then reported 39 in their second catalogue, making 50 reported events overall. So this diagram shows compact objects that we know about in the universe, including the LIGO and Virgo observations. And we clearly have a lot of these observations. But the problem is that we still aren't sure how these mergers are forming, since it's quite hard for 2 stars to become a compact binary that merges within the age of the universe without destroying each other or becoming unbound during the course of their evolution. So where do all of these binaries come from? Well, there are 2 main channels that binary merger formation scenarios fall into. There's isolated evolution and dynamical evolution. So isolated evolution occurs when 2 stars are born in a binary and evolve together, undergoing some mechanism that allows them to become close without merging before they become compact objects. And because these binaries evolve together over a long time, they settle into energy-efficient circular orbits. Our other option, dynamical evolution, occurs in very densely populated regions of space, like active galactic nuclei and star clusters. And in star clusters like globular clusters, the mass segregates. So you get a dense core full of dark compact objects which can interact and become bound to each other. And in such a dense environment, black holes can merge dynamically, and that looks something like this simulation by Johann Samsing, which shows the kind of dynamical interaction that might take place in a globular cluster core. So it's showing a pair of black holes interacting with a third object and losing kinetic energy to that third object, which shrinks the separation of the binary. And as the interactions continue to play out, you'll notice the binary orbit is getting less and less circular, as well as getting closer. So repeated interactions of this kind can lead to a rapid shrinking of the binary, and then the binary can merge before it has a chance to interact again. And this can happen very, very fast, and as little to 4 days since the previous interaction. And because these binaries merge so quickly after they become bound to each other, their orbits don't have time to settle and become circular. So dynamical interactions can give us mergers with higher eccentricities than isolated binary black holes. And in fact, simulations by people like Johann Samsing tell us that about 5% of globular cluster mergers should have an eccentricity of about 0.1 and above when their signal reaches the detector at about 10 Hertz. So on the left here, you can see a sketch of the kind of quasi-circular signal that is typical of an isolated binary. And on the right, you can see a moderately eccentric waveform with an eccentricity of 0.2 at 10 Hertz. And it has this wobbling shape because there's a stronger burst of gravitational waves emitted when the binary is closer together, but this decreases when the binary becomes further apart again. And in my analyses, because of the waveform model that I use, I can only look at eccentricities up to 0.2. But for illustrative purposes, I've also included a sketch of an even more eccentric system with an eccentricity of about 0.9 at 10 Hertz. So how do we measure eccentricity? Well, I'm not going to go into much detail at all on our method, but what we do involves a Bayesian inference software library, primarily developed at the university that I work at Monash, and this library is called Bilby. And if you want to see a little more detail on the method, you can scan the QR code on this slide and see it on the poster. Or if you want to see it in a lot more detail, you can read the 2019 paper noted in the bottom left. But basically, eccentric waveform templates are trickier to work with than circular templates. So we have to have a workaround that involves running Bayesian inference with a quick circular waveform and then post-processing these results using a likelihood reweighting method that was first demonstrated in Payne et al. 2019 with our eccentric model. And what have we measured? Well, from the first transient catalog, we found that none of the 10 binary black hole mergers had any support for significant eccentricity. So here I'm showing the 90% confidence upper limits on eccentricity plotted against the chirp mass of the binary. And this result is actually consistent with both the isolated and the dynamical formation channels, since, as I mentioned previously, we expect only 5% of globular cluster mergers to have eccentricities greater than 0.1 at the detector. And that is 1 in 20, and we have only 10 events here. But can we solve the formation channel mystery with all the new events in GWTC2, the second transient catalog? Well, our analysis for this is still ongoing, but I have plotted the 2 events of interest that I've looked at individually so far. So we have 190425, which is a heavy binary neutron star. And I've plotted the 90% upper limit on this. So that's in pink, and 190425 is not detectably eccentric. However, 190521, which is the most massive binary black hole so far detected in gravitational waves, the arrow shows the 90% lower limit. So under the caveat that we can't include spin-induced precession in our eccentric models, this binary does look like it had significant eccentricity. So this result implies that our mergers could all be dynamically formed, and we could even hope to see a couple more eccentric mergers in GWTC2. And then we could hopefully make more confident statements about how LIGO and Virgo's binaries are forming. So just to summarize my talk, eccentricity is important for telling us about binary compact object formation and merger environments. It can be useful to tell us about individual events as well as about populations. We may well have detected one eccentric event already, but we hope that our 038 analysis will bring even more. And in the more distant future, third generation detectors may allow us to use eccentric binaries to map the formation and evolution of globular clusters in the universe. And I've actually recently submitted a paper to monthly notices demonstrating how that can be done. And we're just working on responding to the referee comments now. So thank you very much for listening.
Thank you very much, Isabel. So questions again at the very end. We move on now to Heidi Thiemann, and her talk is Red Novae Candidates, an investigation of long period near contact giant binaries. Thank you, Heidi.
Hopefully you can see my screen here. That's it. Someone let me know if not. If not, I will continue. Okay. So hi there, my name's Heidi Thiemann and I'm a final year PhD student from the Open University. I'm working in the School of Physical Sciences where I've only got a few weeks left. And today...
Sorry, Heidi, I can't see your presentation.
Well, that's annoying, isn't it? 1 second, let me try that. Problem having too many screens. Can you see this one?
I can see that one, yes, okay.
Fab, okay, well that's the introduction done. So there we go. I'm going to be talking about some stars that I'm quite interested in. These are near contact red giant eclipsing binaries, and I'm going to be talking about them in the context of how we discovered them, kind of some spin-off projects, and whether they could be the progenitors of red novae. So I'm going to start the story with the SuperWASP telescope. And SuperWASP, I'm sure many of you have heard of before, but it's shown here on the right, and it was the most successful ground-based search for transiting exoplanets, having discovered around 200 to date. However, the capabilities of SuperWASP extend to far beyond exoplanet detection, and actually it's been really successful in the field of stellar variability. So over the 11-year operational lifetime, SuperWASP surveyed almost the entire night sky, excluding the galactic plane where the stellar density was simply too high to resolve individual objects given the fairly large pixel scale. So you can see the sky coverage that SuperWASP had in the image on the left. Now, during this time, SuperWASP took a huge amount of data, and the final photometric archive contains around 580 billion data points, corresponding to around 31 million unique bright stars, monitored with a fairly high cadence and a long baseline. So starting in 2015, my supervisor, Andrew Norton, who I think might be here today, began a reanalysis of all 31 million light curves in the SuperWASP archive. This took around 2 years to run, or 90 CPU years, and the aim of this reanalysis was essentially to search for all periodic variables in the SuperWASP archive. And the analysis itself was sensitive to periods in stellar variables between around 1 hour and 1 year. So as a result of this analysis, he identified around 8 million potential periods in around 3 million objects. However, as you can see from the plots here, on the ones on the left show the kind of unfiltered view. So there's a significant number of here which are close to integer fractions or multiples of a sidereal day or a lunar month. And these periods are most likely to be spurious and caused by systematic noise to do with the telescope. Discounting this noise, if we move to the right, we're left with around 1.6 million possible real periods in around 0.7 unique stellar variables. Now, this is quite a lot of data to go through, and trying to find any sort of individual objects felt a little bit like trying to find a needle in the haystack. So one way we actually went to solve that solution, or solve that problem even, was to upload all 1.6 million potential periods to the Zooniverse, a citizen science platform where anyone can get involved in real science. We created a project called SuperWASP Variable Stars, and in this project we simply asked the public to look at SuperWASP light curves and classify the type of variable star that they belong to. It's a very simple pattern matching exercise, so we show a volunteer a light curve and ask what type of variable star. Is it a type of contact binary and a detached eclipsing binary, is it a pulsator, a rotator, etc., etc. So with this, our aim is not just to identify the weird and unique variable stars, but actually to create a publicly available online dataset and do various other works, population studies of variable stars. Now, my colleague Adam McMaster is actually working on using this output of the SuperWASP Variable Stars project to create this database that anyone can access, but that's going to be work that I'm going to have to leave him to talk about on another day. So what actually came of this project, though, was something very interesting, and this is the kind of main part of what I want to talk to you today and my post from earlier in the year or last year. So very early on in setting up the SuperWASP Variable Stars project, we identified this weird light curve shown here on the right. At a first glance, it appeared to be that of a kind of classic eclipsing contact binary star. But for anyone who's worked with contact binary stars can see that it's got a period of around 40 times that of a classic contact binary. So normally you would expect a contact binary to have a period between about 6 hours and 1 day. So to find a contact binary with around 42-day period is very odd. So this seemed to warrant some sort of follow-up, and we were able to obtain a single spectrum of this target using the William Herschel telescope, which appeared to show that the object has passion lines and evidence for it being a double-lined object. Hence, we can tell that it's a binary star with at least one red stellar component. So we can assume that for this previously unstudied star, if it's got a 42-day period and we've got a double-lined object and we've got one red stellar component, the only way that it can kind of plausibly exist is for it to be comprised of two giant stars in or almost in contact with one another. And this is a configuration of binary star which isn't known, so it's something that's quite exciting to look at. Now, one object and one spectra isn't really enough to have much to go on, so our next step was to identify similar objects in catalogue data. We searched the SuperWASP periodicity catalogue and other catalogues like the Assassin catalogue of variable stars, and we enlisted the help of our Zooniverse volunteers to identify a further kind of 26 candidates that we could follow up. Now, the reason that these really were interesting to us, though, is that not just the identification of a new configuration of binary star, this near contact red giant eclipsing binary star, but actually what these stars could become. So due to the kind of assumed instability of the system, the low temperatures, the late stellar types, we believe that these near contact red giant eclipsing binaries could be the progenitors of a rare transient called red nova. Now, red nova are these kind of relatively new class of optical transients, and as you can see from the plot on the right here, they're characterized by kind of the luminosities between that of classical novae and supernovae. They've got comparatively red colors at late times, they've got low temperatures, low expansion velocities, and we do know that they are the result of the merger of a long period contact binary system. So logically, it might be the type of system that near contact red giant eclipsing binaries could evolve to form. And they're also very rare. So within our galaxy, we've only got 4 that have been detected in the last 25 years. So the current scarcity and diversity of observations means that extracting any sort of information about the transients and their progenitors is difficult, and identifying progenitors is a really exciting opportunity to be able to characterize red novae further. So we identified these candidates at the end of 2018, and since then we've completed a 2-year-long follow-up program of photometric and spectroscopic observations. During this time, we basically took multi-color photometry almost nightly using the Open University's telescopes. We got high-resolution spectroscopy from which we could extract radial velocities. And based on this, we confirmed that 12 out of the 27 candidates are long-period near-contact binaries, with false candidates being Cephids, B shell-type stars, and possibly stars being possessed by a third body. Now, if we combine the multicolor photometry with the radial velocity measurements, what we can do is we can model the parameters of the stars, the masses, the radii, the temperatures, etc., of the stellar components using the Phoebe package, which implements the Wilson-Davini code. Now, this means that we can take our confirmed binaries and actually confirm that they're near contact red giant eclipsing binaries. And what we found is that 12 of the 12 systems that we modeled, 9 appear to be semi-detached system where one star is kind of filling or overflowing its Roche lobe, and 3 are definitely systems which are in contact with one another, so they're surrounded by a common envelope. So what we found here is that we've modeled 12 binaries. They're all made up of late type giants with low temperatures, relatively small separations, relatively low masses. So that's really successful. We've confirmed that they're near contact red giant eclipsing binaries. Our next step has been in modeling, and we've been trying to understand the birth and the death of near contact red giant eclipsing binaries using 1D stellar evolution models. What we found is that the systems that we're seeing at this very moment in time must have begun their life as long period detached binaries which have evolved to be red giant binary twins. Then, following the formation of a common envelope, the binary experiences this rapid inspiraling event where the system essentially experiences some extreme mass loss on a very short timescale, where they blow the mass out of the system. What we're not quite sure of yet is whether they actually form a red nova as a result of that, or whether white dwarf binaries are formed. So what we're seeing at the moment, these current red giant binary twins, we believe that they could be on the brink of this kind of rapid inspiraling event. But what I think is most interesting is that for this sort of evolution to form, and for these stars to be almost identical throughout their entire life, the mass ratio of the binaries must be almost exactly 1-to-1, or within 1% of that. So they're extremely rare systems. So that hasn't quite helped us answer the question of whether they are red novae. So a few questions remain. We don't quite know whether we've caught them in a very short system where they're, or kind of short phase of their life where they're about to have this inspiring event. We're not quite sure what the red nova event looks like or the common envelope event looks like. We can give it a best guess, but I'm about to finish my PhD, so hopefully that's someone else's research that they can focus on. So I'm going to summarize by basically saying that SuperWASP still remains to this day a really valuable archive for variable star research. And through our Universal Citizen Science project, we're going to make this kind of full archive available to the public, to pro-am astronomers, to researchers as well. So watch out for the development of that. We've managed to identify some really fascinating targets, these kind of these near contact red giant eclipsing binaries. We can't conclusively say that they're red nova progenitors, but we can say that they're interesting and worth following up, and hopefully that'll be someone's research in the future. So I'll end it there now and pass it back to you, Paul.
Okay, thank you very much, Heidi. And our next speaker is Nuria Jordana Mitians. What is the role of the magnetic fields in GRB outflows, the case of GRB 190114C?
Hi, my name is Nuria Jordana, and I'm a PhD student from the University of Bath. And in this talk, I will give brief insights on which is the role of the magnetic fields in these gamma rays boost flows and mention the case of GRV 190114C. So I will start with what are they, how are they detected, and then I will move to talk about how early time polarization observation can distinguish between magnetized and baryonic jet models, and how this early time emission is highly polarized. We know this already, but this also evidences this large-scale magnetic field ejected from the central engine and favor these mildly magnetized jet models. Then I will mention this case, this GRV called 190114C, which was one of the most energetic GRVs ever detected. It was detected in the sub-electron volt domain. And the only issue is that these observations, these polarization observations, contrast with previous ones because the polarization was very low seconds after the burst. So what are GRV? GRVs are brightest species of gamma rays in the universe, and they are also theoretically challenging because they are tests of strong gravity magnetic fields with material ejected at velocities close to the speed of light. They are also extragalactic objects, and they are formed when there is a massive star collapsing or where there is the merger of two compact objects, such as neutron star binaries or neutron star black hole. The accretion then to these newborn compact objects, such as a black hole or a magnetar, powers two bipolar and relativistic jets. There is two kinds of emissions that we detect. We detect emission from the gamma ray prime or emission from the afterglow. The gamma ray prime mechanism is less well understood than the afterglow, and there is two competing mechanisms. We have internal shocks, shells of different velocity colliding with each other, releasing kinetic energy, or we have magnetic dissipation mechanisms such as reconnection. Then when the jet collides with the interstellar medium, this material gets decelerated, producing a forward shock and a reverse shock. The key point here is that reverse shock travels backwards into the jet and still contains the properties of the central engine. And forward shock is basically shock ambient medium. They are detected by their bright gamma ray flash, because the jet is also pointing towards the observer. So it's pointing towards the gamma ray satellites, such as SWIFT. Basically, then the jet is never edge on, but face on. So currently we are detecting about 200 GRVs per year. And the nice thing with these gamma ray satellites is that they trigger real-time alerts. So here in the middle picture, you can see how the Milky Way is in red. And we have also a big red and white dot that pops up. And it's basically because the GRV has outshined any other source of gamma rays in the universe. So when there is these real-time alerts, this triggers a follow-up campaign with ground-based telescopes. And depending on which telescope you use, if you use large telescopes, this needs manual trigger of observations. And this also means that their observation will start hours to days after the burst. However, with the use of these robotic telescopes, they do not need human intervention, and we can start the follow-up. So we can get the emission from the reverse shock optical probe too. Here on the right, on the bottom right, you can see a case of a GRV detected. So it's basically point-like. It's a point-like source that gets brighter and then fades away. With polarization, then what we do is we have an extra dimension of information, and it's also a proof of the structure of the magnetic fields in the emitting region. So basically here on the right, you have that the main candidate emission is synchrotron, and synchrotron can be 70% polarized in the lab with a large-scale ordered magnetic field. However, if this large-scale magnetic field is distorted due, for example, to relativistic aberration effects, or there is overlapping of different emission components, this can get further reduced to zero. Pioneering observations of polarization measure 1-3% during the forward shock, and this proves the large-scale jet geometry and the ambient medium, such as the dust properties of the host galaxy. Then on the right, you can also see the jet models. So basically, depending on which is the role of the magnetic field, so what rules the outflows dynamic, if kinetic or magnetic energy, we have several options. Baryonic jets will not have polarized from reverse shock or forward shock. And in the case of mildly magnetized jets and highly magnetized jets, we will measure polarization. The mildly magnetized jet, we will measure polarization for the prompt and the reverse shock. And in the case of the highly magnetized jet, only for the PROM, because it's likely that the magnetic reconnection will break all the structure of the magnetic fields, and then the reverse shock will not be highly polarized or not polarized at all. With the appearance of these gamma ray observatories with polarimeters, they measure 70, 90%. And thanks to the use of these robotics telescopes, we could measure in the optical 30, 10% for reverse shock. So this mildly magnetized model was favored. For the case of the GRB from 2019, we got data from two collaborations. This was a joint effort from Master Global Robotic Net and also the Liverpool Telescope. Here you can see master data on the right. And basically our observation started just 30 seconds after the burst, and the polarimetric data started 50 seconds after the burst. In this case, it was very nice because we got data from two master sites, from Canary Islands and the other one from South Africa. As you can see here, the polarization was 8%, and then it suddenly dropped to 2%. With the data from the Liverpool Telescope, we got data as soon as 200 seconds after the burst, and it was nice too because we got data in 3 optical bands. And what the data showed is this kind of flattening in the optical light curve, and also this constant 2% in polarization. Additionally, you can see here in the middle panel the optical photon index. The optical photon index is basically the steep of the 3-point band spectrum. So it can tell you the synchrotron spectrum in this case. It can infer information from this. Then we modeled the light curve in terms of reverse and forward shock model. And it was interesting because we could see how the forward shock synchrotron frequency was crossing the bands. So this was a hint that if we were in a case of a reverse forward shock model. And also the optical photon index showed this kind of decreasing behavior, which is not expected only from forward shock. So we could guess that there was an extra spectral component. Then the issue was why the polarization is for the pure reverse shock is so low, and it's only high in the very beginning. So putting all this information together, we get the photometric data on the upper part and the polarimetric data in the bottom part. So basically with the modeling of the emission, this gives information about the strength of the magnetic field. And also basically because reverse shock emission still has the properties from the central engine, we could model it in terms of their brightness and see that the reverse shock was expected to be 70 times more magnetized than the forward shock. And this hinted us that this large-scale magnetic field existed. Then for the case of the polarization observations, this gave information about the structure of the magnetic field. And this 8%, we suggested that it was contamination from the PROM photons, because as you can see in the bottom part, the PROM was quite extended. And the 2% was dust induced because of the highly obscure environment in the host galaxy. Then the problem is why there is no polarization for the reverse shock. And we suggested that this large-scale magnetic field was being distorted during the prompt emission. So we suggested magnetic dissipation mechanisms such as reconnection. And this was a case of a highly magnetized jet. Finally, I will end my talk with this plot, which shows the state of the art of the more relevant polarization measurements in GRBs. And as you can see here, you can basically access the jet physics during the first minutes after the burst, because later on you lose all this information. And I will end this talk with a statement saying that current observations favor these mildly magnetized jets. However, we got this case of a very energetic GRB in which we thought that it was completely highly magnetized. Thank you.
Okay, thank you very much, Nuria. Now we have the final talk, which is from Shannon Jones. I've got a video to show of Shannon's presentation. Give me a few seconds to switch over and share my screen. Okay, I assume somebody will let me know if you can't see that.
Hi, my name is Shannon Jones and I'm a PhD student at the University of Reading. Today I'm going to be talking about the visual complexity of coronal mass ejections, also known as solar storms. Coronal mass ejections are huge eruptions of plasma and magnetic field which travel near radially away from the Sun. If these storms reach the Earth, they can cause devastating impacts such as long-term power cuts, loss of aircraft communication, and satellite damage and failure. How do we observe CMEs? There are many different spacecraft which image and measure CMEs. These include the NASA twin stereo spacecraft, which are in orbit around the Sun. Stereo A is in an orbit slightly ahead of the Earth's orbit, and Stereo B is in an orbit slightly behind. Heliospheric imagers have a very wide field of view. These image visible light Thompson scattered by free electrons. Each point in the image represents all the material seen along the line of sight. This means that pixels appear brighter if there is more material in the line of sight, or if the material is closer to the Sun. These images are usually running difference to make the CME structure appear clearer. Here is an example movie showing a CME travelling away from the Sun in running difference heliospheric imagery. In these images, light regions can be interpreted as an increase in mass along the line of sight between the two original images. Likewise, dark regions can be interpreted as a decrease in mass along the line of sight between the two original images. CMEs usually have a bright storm front at the leading edge, and behind this they have a wealth of internal structure. CMEs appear very different in these images. These differences are easy to see, yet difficult to quantify. For this reason, we decided to set up a citizen science project to investigate the differences between CMEs using human perception. Our citizen science project was created using the Zooniverse platform in collaboration with the Science Museum to raise interest in their exhibition on the Sun. This is a screenshot of the project homepage. The project was called Protect Our Planet from Solar Storms. We showed people two solar storm images side by side and then asked them to decide which one looked the most complicated. We showed participants images of 1,110 different CMEs and asked 12 people to look at each pair of images. In total, 4,028 citizen scientists took part, resulting in more than 200,000 classifications. We then used the data from our citizen science project to rank all the CMEs in order of their visual complexity. To do this, we fitted a Bradley-Terry model to the data. This works by randomly assigning a reference CME and deciding how complex each CME is compared to that one reference CME. This model is widely used in psychology and is a variant of logistic regression. Here are a selection of CMEs from the ranking. The 3 CMEs in the leftmost column are not complex at all, and the 3 CMEs in the rightmost column are very complex. This clearly shows that CME characteristics change throughout the ranking. Here is a word cloud showing the characteristics the citizen scientists said they looked for when deciding which CME was the most complex. As you can see, messiness was the most talked about characteristic. But there were many other factors which influenced their decisions, including the CME size, shape, and the number of storm fronts. Does visual complexity change over the solar cycle? It's well established that the Sun has an approximately 11-year solar activity cycle, most noticeably in the number of sunspots on the Sun. The occurrence of CMEs follows this pattern, with more CMEs occurring at solar maximum and fewer at solar minimum. Recent studies have also found that CME width, speed, mass and kinetic energy all vary with the solar cycle. So this plot shows how the visual complexity of CMEs changes over the solar cycle. The top panel shows the complexity of every CME, with pink dots representing CMEs observed by stereo A and blue dots representing CMEs observed by stereo B. The average annual means and standard deviations are also shown. The bottom panel shows the daily sunspot number and the yearly mean sunspot number. As you can see, visual complexity clearly varies over the solar cycle. This also shows that the average complexity of stereo A CMEs is significantly higher than the average of stereo B CMEs. But why is the average complexity so different between two supposedly identical cameras? This plot shows the visual complexity of 188 CMEs, which were simultaneously observed by both spacecraft. 149 of these CMEs appeared less complex when observed by stereo B. This suggests that there are differences in the instrument characteristics between the two spacecraft. Another possibility is that CMEs appear smaller in stereo B images, as the spacecraft is slightly further away from the Sun. Next, we looked at quantifying visual complexity. CME size in heliospheric imagery is described in terms of angular width and degrees elongation. All the images in the project were chosen so the CMEs had reached a similar elongation, but the CMEs still varied in angular width. As it turns out, CME width is correlated with visual complexity. To measure CME brightness, we masked out the image background and counted the number of bright pixels in the CME. A pixel is bright if its value is in the highest eighth of the colour map. We normalised the brightness values by each CME's angular width and found that brightness is also correlated with visual complexity. Our results suggest that there is some predictability in the structure of coronal mass ejections, which may help to improve future space weather forecasts. However, further research is needed to investigate what is causing CMEs to appear different. Is it the complexity of the CME's source region, or structure in the solar wind, or multiple CMEs combining perhaps? To summarise, CMEs can appear very different. We set up a citizen science project where people compared CMEs. We ranked 1,110 CMEs by visual complexity. We found that the annual average visual complexity values follow the solar cycle. Complexity is associated with CME width and brightness. And our results suggest that there is some predictability in the structure of CMEs. Thank you for listening. I hope you found this presentation interesting. If you have any questions, please email me at s.jones2@pgr.reading.ac.uk.
Okay, so thank you to all our speakers. We have questions now for our first 4 speakers, and Shannon has said that she's happy to answer questions by email. I'll pass you over now to Pamela for the questions.
Okay, I have a question for Heidi, which is so cool to see such a citizen science. How many people got involved in the classification so far, do you know?
Hi, thanks for the question. So at the time I did an initial analysis back in September 2018, we had around 4,500 registered volunteers. I checked it this morning actually just to update my thesis, and we've had almost 9,000 registered volunteers get involved. And that doesn't include people who maybe haven't registered with this Zooniverse platform. So we've had quite a wide reach from around the world, which has been really satisfying.
Thank you. Our next question is for Soheb, which is, what a lovely talk. Did you animate neutros yourself?
Yes, I did. Yeah, so I used a 3D modeling program, Blender, to create a 3D model, and I rigged the system, which enables the mouth to move following any given dialogue or script.
Thank you. Don't forget to post your questions in the chat or the Q&A. We've seemed to have an interesting focus on GRBs here and gravitational waves. For any of the speakers, what did you find most interesting in the other people's talks?
Well, for me personally, I think learning about the actual mechanism behind a GRB was really fascinating, and then also combining that with the formation of gravitational waves from Isabel's and Nuria's talks. I think it's really cool to see them kind of unified and come together. From one single event, you can get all this different information. So I think that's really cool.
No, I was just going to say, I really enjoyed the fact that there was a huge contingent of both citizen science and binary stars. So I'm just impressed by hearing about all of them. Love it.
Yeah.
Yeah, I agree. I think it's really exciting that like this field is kind of fairly new and we're all kind of working on similar things and driving the progress. I think it's really cool.
Nuria?
Yeah, in my case, yeah, it was really interesting to see the connection, like the three in the three cases, and how you can choose from a single event, choose many phases of it, and different science in this case.
Brilliant. I was very interested in your very rare red giant binaries, Heidi. So you found 26 of them so far, yes?
Well, we found 27 candidates, which we thought could be red giant binaries. Managed to get rid of about half of them, finding that they're Cephids, just masquerading as binaries. Kind of helpfully radio velocity sorted that out. A few quite interesting shell stars as well hidden in there. But yeah, we've got a nice selection of 12 near contact red giant eclipsing binaries, which might merge and become red novae. We'll see. Might take a few mega years to do that.
Thank you, Heidi. And there's a question here for anyone, which is anyone working with magic telescopes on La Palma on their projects?
Yeah, not really in my case. I just, in my case, that GRB was detected by MAGIC. It was the first one that was detected at sub-3 electron volt energies, but I just used the polarimetric data in the optical. So it's complementary, but I didn't use it in this case.
And no one else?
No.
No. Okay. The GRBs that, the short GRBs that have been sent out of their galaxies, do you find that to be dominant for the short GRB mechanism, or do you find it other mechanisms for short GRBs?
So this is an interesting question. So when we detect short GRBs, what we're really detecting is a burst of gamma ray radiation. And what we found is that, at least from nearby sources, so within 10 megaparsecs, you can get these magnetars, which give off giant flares, which contain short bursts of GRBs as well. So whilst these aren't SGRBs, like we know them, they do get registered as GRB detections. So in the sample of SGRB detections that we have, it is possible for these magnetars, giant flares, to to kind of reside and hidden within these samples. It's a tricky one. It's kind of hard to tell them apart. But these giant flares, they last less than a second, so that's one way we can kind of hone in on these other GRB sources that could fall into this category.
Thank you. And the next question is for anyone working with LIGO, which is, what is the current estimate for the number of BBH, BHNS observations per annum by LIGO, etc.?
So for BBH, it's on the order of hundreds at the moment. Can't reveal too much about what the current detections have been, but yeah, on the order of hundreds. For the black hole neutron stars, it is less. We expect to detect less or fewer of those. I guess on the order of kind of 1 per annum at the moment. But yeah, the sensitivity is improving all the time. And when 04, the fourth observing run starts, that number will again increase for both of them, because we'll be able to see further out into the universe and detect more things.
Thank you very much. And someone has sent a message saying that's significant. Wow. We're at 5:29, and I believe we're due to finish about 5:30. Is that correct, Paul?
Yes, that's about it. Yes. Any more pressing questions?
That's all the questions that we've received so far.
Okay. Thank you very much, Pamela. And thank you again to all our speakers on the panel here, and to Tom earlier on for his talk. Just a reminder again that the AGM of the Society will take place at 4 p.m. on Friday, the 14th of May. And because the next meeting is an AGM, the next monthly A&G open meeting, the next ordinary meeting of the Society, will be on Friday, the 8th of October this year. I hope to see you all at the AGM. Thank you very much, everyone.